Let's talk about why we even want to do feedback at all in our feedback controls, which is what automatic controls or control systems is pretty much all about. And let's also start talking about a new performance measure called steady state error. Up to now, the performance measures we've been talking about are measures of the transient response of the system. What happens between time zero and before the system settles. Steady state error is a steady state performance measure after it settles as time goes to infinity. But anyway, hold on here. There we go. There's my laser. First, let's look at what's called open loop control. That's where there is no feedback. You just give an input. Your system is what the system is, and it has some output. If you know how the system works, you can get the output you want by giving it the input you want. Unless there happens to be some other input you have no control over. If we were talking about the speed of a car, for example, you desire a certain speed, what the actual speed is, there might be some throttle setting for nominal conditions that for each speed. For each speed, there's a certain throttle setting, and you'd get the speed you want. But what if you're going up or down a hill or into or against the wind or things like that? Disturbances you can't control. So let's look at that. And we'll keep things simple. We'll make this process just a first order process with this transfer function. And these inputs are just steps, meaning constants. Go from zero to some constant at time zero. The total output will be the sum of the outputs due to each input. We know how that works. Transfer function times the input gives us the output for that input. Take the inverse Laplace transform, and here's what we get is the output. The error is the difference between the desired input and the actual output, or the desired output and the actual output. And well, it comes to this. As time goes to infinity, it's just minus t sub d. If there were no t sub d, there would be zero error. If there were no disturbances, there would be no error. But with the disturbances, the error exists, and it's as big as the disturbance itself. So now let's look at it with feedback. And here's a great diagram that you should just implant in your head. This is the quintessential control system feedback system. We have a process or a plant. Some textbooks call that plant. And usually we can't do much about how the plant works itself. That would be redesigning something. We could do it, but that's different than controlling the thing. Redesigning the thing is different than controlling the thing. If this were a car and we were talking about cruise control, this is the way the car responds to throttle and other things like whether you're going in the wind or against the wind and that kind of stuff. That's just sort of the physics of the car. Now we take, well, the actual speed we sense it with some kind of mechanism. So there might be errors in that mechanism, tachometer, but our sensed speed gets fed back compared to our desired speed. And that difference will make a difference in this controller. The controller says how much throttle we give it. And then there's again the disturbance. So let's look at everything the same way. We'll make this G the same first order system as in the open loop case. This R and this T sub D will just be steps again. And we'll just make this G sub C and this H just constants. So we get to pick these things, these two constants. Let's see what happens then. And we'll ignore noise, this little experiment. We'll look at two different transfer functions because we have two different inputs. Y over R, the forward loop, and by the way, everything up here is the forward loop gain. It'll be these two things multiplied, the product of these two things. And this is at A over S plus A, and this is the constant G sub C. So we'll have G sub C times A over S plus A over 1 plus all that times H, right? Remember how the way block diagrams work? That's what I just said. It simplifies to this. With Y, you need to know how to do this. I'm going through this because students have trouble with this. I shouldn't say with Y, with Y over T sub D, the disturbance to the output. Damn, I keep going the wrong way. This G is forward loop path. The product of these two things is the feedback path. So we're going to have a G or an A over S plus A over 1 plus that times these two, which simplifies to that. You add those two together, or you with the Y's, it'll be the sum due to those two inputs separately. And because they are steps, it'll be R over S and T sub D over S. Added those two inputs. If you did some partial fraction expansion, you get to this. And if you inverse Laplace transform, you get to this. The error would be little r minus y. And as t goes to infinity, this part goes to 0. So here is error in the time domain as t goes to infinity, as time goes to infinity. If we make 1 plus G sub C H equal to T sub C, the R terms would cancel. And there'd be no error due to just the R part. And you're left with this. So if we choose this, we make any error due to R go away. And we're just left with this as the error. Before, with open loop, it was just minus TD. Now it's minus TD divided by G sub C. We can make the error as small as we want by making G sub C as big as we need. And H would also have to be chosen to make this true. I think that means H equals 1 over G sub C. But we can make the steady state error arbitrarily small by picking those two parameters instead of just being stuck with total disturbance, error due to disturbance. That's why we want feedback. And we talked about a new performance measure. All the other performance measures we talked about up to now were in this transient phase, transient response up to when it's settled. In the next video, we'll start talking more about the steady state error. And I'll save that for another video.